guys, it's IDW, and today we're going to be doing a lot of work for a barrel shifter. Because although one of the inputs is already being sent directly in, as we finished off last time, there's still a lot of messy stuff going on with this other input. And overall, there's several things that we don't want it to be able to do that it can currently do, like different really weird OR functions, like if I unpower this lever and this lever, that's going to make it so that it's the OR of the number shifted left once and shifted left twice, and that's not really the most useful function, frankly. And yeah, so we really don't want to do all of those. And another problem that we have is that there are some functions like getBit that this thing just can't do. And we're going to need to set this thing up so that not only can it do getBit, but it can also do all sorts of other normal barrel shifting operations in some sort of pattern. We're going to need to assign different input configurations to different barrel shifts, and this is going to get really, really messy when we consider that this hardware that's going to be used to decode this is going to turn out to be really time critical for making this entire thing really fast. And yeah, so overall, this is just going to be a whole lot of theory and number crunching that we're going to be doing today to explain why the decoder that we're going to end up using is going to work for this thing, and we're going to be building some of it, not as much as I maybe would like, just because I need to make sure that it's clear what I'm doing for all of this. But don't worry, because there is in fact a plan, so let's talk about that now. So before we talk about the actual configuration, let's talk about how you can create one of your own. If you're ever in a situation where you need to create a monstrous decoder like this. So I've talked before in this series about the importance of design decisions, and it's going to be really important to be objective when we make those, as I've talked about before. So let's think about what we actually want to do with the barrel shifter. Well, the first function that we want this computer to be able to do really quickly that probably requires a lot of advanced barrel shifter functions is software multiplication. We don't need this function quite as much for this particular series, but it's going to be something that's going to be important for us nonetheless. Sorry about that. I decided that my fan was going a bit loud, so I tried to turn down some of my video settings because we really are just staring at this and just talking about how this needs to work. But anyway, so like I was saying, we don't exactly need multiplication so much for the functions that we're going to be implementing, but it's going to be useful for other things nonetheless. First of all, if we want to speed comparisons with other computers, the standard for that is usually multiplication operations, specifically floating point multiplication operations. And we're going to want to be able to use some sort of standard to compare, and so if we actually have a multiplication function, then we can actually compare it. Now, another good reason is that software multiplication, even though we're not going to be using it so much for this series because we're going to be doing really simple graphical processing, if you get into more advanced stuff, having software multiplication or just any sort of multiplication in general is going to be really, really, really vital. So maybe eventually I'm going to redo this series where I just add some more microcode that does some extra functions, and if I do that, then multiplication is going to be something that's very useful for that. Or if we want to add some in this series even, just because that's how much flexibility microcode gives us, but it's just very important that we just already have a multiplication operation. So in order to do this software multiplication we've been talking so much about, there's two barrel shifter operations that we're going to need. First of all, standard bit shifting, because when you're calculating each partial product, that requires what's it called? That requires just shifting the number over. And the other thing that we're going to need is we're going to need getBit. And getBit is basically just a function that takes the value of one specific bit. So if I did getBit 2, that would take bit 2 and it would give that as an output. And what we'll do with that is we'll use that as predicates to and the, I'm getting a bit technical here, but we're just going to need that information available to us, and getBit is a function that makes it available to us like that. So that's two shifting functions that we need, but that's not all we're going to need, because bit shifting is going to be really useful for moving scan lines around on the screen. Now, we haven't exactly covered this yet because this is a bit more into the software that we're going to be implementing later, but let's just think about it this way. What we're eventually going to be doing is we're going to be transferring binary bits to our screen. And what that's going to mean is that we're going to select some part of the screen and we're going to send an 8-bit number to that part of the screen, and that 8-bit number is going to set the state of each of those pixels. Now imagine you want to move those pixels without moving the origin. What you can do is that you can left shift and right shift it to move it, but that's not the only thing that you're always going to want to do, because sometimes you might want to rotate it as well, in which as the bits go through the upper limit, they come out through the bottom again. So another function that we're probably going to want for this thing is bit rotation, as well as both left shifting and right shifting. Now, one interesting thing about the rotate function is that technically a rotate left once function is the same as a rotate right 7 times function, because if you think about it, the bit configuration stays exactly the same. So it's just which one of the positions that each bit moves to. So that means that we don't need to have two separate rotate left and rotate right functions. We can just have one rotate left function that is all-encompassing. So if we count up all of the functions that we just described, there's really 4 that we have in total. Shift left, shift right, rotate, and getBit. And those are going to be the 4 barrel shifter operations that we're going to do. And it's also nice to note that these shifting operations also are somewhat universal, and they can be used for all sorts of other things that we're not going to use them for, but it's just nice to know that there are actually other things that we can do with this barrel shifter other than the actual things, which is usually the case, but we still like to try to focus on doing specific tasks. So, now, very conveniently, for every single one of these different types of shifts, there's exactly 8 different shifts that you can do, because at least if we count shifting 0 times, which we are going to end up doing as one of the shifts. So for example, if I'm shifting left, then I can shift left 0 times, 1 time, 2 times, 3 times, 4 times, 5 times, 6 times, or 7 times. And that means that that's the same number of shift operations as a rotate function, and it's also the number of operations as in getBit and shift in the other direction, which means that we can sort of unify them all into 3 bits of information that tell us how many times we're shifting, and then we can have 2 bits that determine what kind of shift it is. And that's going to end up being the sort of input format that we're going to have. So let's take a look at that, and when we look at it, we're also going to consider the inputs that we have to the barrel shifter, because ultimately what we need to do is we need to decode this 5-bit input format that I just described into some sort of way to turn on and off these wires. So I'm not actually in Minecraft right now. I'm actually looking at a screenshot of this just because there doesn't need to be any sort of talking going or moving around. We're just going to be looking at this sort of grid that I have here. It's a bit hard to see what's going on, but it's just a standard ROM setup. The decoded shift inputs are the input wires to this decoder, and the desired barrel shifter inputs are the output wires. And what we're going to need to do is create a circuit that doesn't decode every single wire, but still gives the same results as this decoder would. Now, normally when you have a situation like this and you need to calculate a whole bunch of logic, you would use a process called Karnaugh mapping. And that will basically just give you a set of outputs that just contains every single logic gate that you need to do with your inputs to get the desired outputs. Now, I'm not actually going to do this because it's a bit complicated and this episode's already just going to be a lot of abstract stuff and I don't need to explain that. But if you really want to, if I get enough requests, I will make a tutorial on how to do Karnaugh mapping. But I'm also lazy, so that's another reason I didn't do this. So instead of doing that, what I decided to do was try to look at the different outputs that I needed and figure out which inputs corresponded to them. So let's work through all of the inputs to the adder that we have. First, there is the adder shift, which is used for shifting the number an odd number of times. Just to review, the barrel shifter can only do even shifts of the bits, multiple of 2 bits over. So to shift an odd number of times, we need to use the adder to shift once at the end of all of those even shifts. And it just so happens that the least significant bit of this all, the first bit of the shift number, will actually tell us if we're shifting an even or odd number of times. So we don't need to do any processing with that first bit, we can just send it directly into that adder shift bit. So the next thing we need to consider is how to get this barrel shifter to do the rest of the shifting other than just that simple one. And that can be done for the most part by just decoding the next 2 bits in the amount of shifting to be done. Now, one really important thing about this decoder is going to be the way that we're going to be decoding right shifts, because it's going to be a bit counterintuitive. And this is going to be because the rotate function is technically rotate left. So the way that we create the rotate left function is that we do the shift to the left and then OR that with the overflow bits shifted to the right. So the number of times that you need to shift the overflow bits to the right is the problem. If you rotate once to the left, then you need to rotate the most significant bit 7 times to the right so that it arrives at the least significant bit. So if we want to use the same decoder to code the right shift instructions as the ones for the rotates, then counting has to be reversed for the right shifting ones. This is going to be a bit inconvenient, but it's ultimately something that we can just deal with. So if we take that into account, we can create a decoder for the next 2 bits. So now we have the first 3 bits of the input, and we're already like 60% of the way done, and we've just basically done a decoder and sent one of the wires through. And now we're going to need to do a bit more difficult stuff, because sure, we're decoding where exactly everything needs to go to, but we're not always going to want to be doing certain shifts, like if we're shifting left versus shifting right. By default, all of the barrel shifting is going to be going on at once, so when we OR them together, it's going to make a rotate, and sometimes we just want to be doing the right shifting part of it, and sometimes we just want to be doing the left shifting part of it. So we're going to need to decode those last 2 bits to determine which ones of those functions that we actually do. And this turns out to be pretty simple because all we really need to do is just connect up some control wires. Now, there is a little bit of annoying thing with this, because this method will work for shift left, shift right, and rotate, but for get bit, things get a little bit weird. Because sometimes, well, actually think about it this way. So the problem with our getBit function is that there's 2 different ways that we can isolate a bit. If it's an even bit, then we shift it until it's in the most significant bit position, and then we use the barrel shifter shift to get it into position 1, and then we disable all the other bits to just let that one through. On the other hand, if it's an odd numbered bit, then we need to shift it down so that it reaches the least significant bit, and then also cancel all the other bits out. So that means that there's two separate processes that we need to do, one of which is going to, what's it called? Or both of which, rather, are going to mean that we're going to need to neglect all of the other inputs. So that's going to be a bit on the complicated side, but it's not going to end up being the end of the world. It's just going to mean that the two more, or when we decode those two most significant bits, it's going to be a bit more complicated of decoding than those first 3 bits. But the thing is that today we're not actually going to be making the decoder for those 2 most significant bits. We're only going to be doing the 3 simpler bits, and then next time we're going to devote the entire episode to setting up the 2 most significant bits of the barrel shifter input. Okay, so now that we've talked about all of this, we can finally actually get around to actually building this thing. Whew, that was a lot of stuff to talk about. Hopefully I didn't miss anything. I shouldn't have, but it's entirely possible. So yeah, let's go ahead and go back into Minecraft so that we can talk about how to actually build these decoders. Alright, there's a few really important things that we're going to need to talk about before we move on, because first of all, they have to do with why this video has been delayed so much, and second of all, there's a few lessons to be learned here that I messed up. There's sort of things that I've already talked about, and I was trying to say, well, this is something you should avoid, and I ended up doing it myself. So yeah, let's talk a little bit about some of the things that have been going on here. So if you look at our ALU, it looks quite different from what it was in the last clip. That's because I filmed the last clip about a month ago. And the reason for that is that I originally thought that I could do something really simple, but it turned out to be a whole lot more complicated than it originally was. And since I've dedicated so much time to it, I think I might as well just explain what it is. It has to do a bit more with some of the future things that we haven't looked into yet, that we will look into eventually, but we can still sort of see some of the general ideas. You might remember that we don't always we don't directly output this output of the ALU back into there. We have to add some delay in there in order to make it so that the entire length of the loop is 16 ticks, so that there's 8 different, I guess we're going to be formally referring to them a lot as cores, even though maybe that's not the best technical definition. But in order to have 8 different cores on this circuit, we need the total delay on this to be 16 ticks, and we add that delay in here. So let's talk about the amount of time that, or actually let's talk about the memory for a second. So let's say that I want to take an output from the ALU and send it directly into memory. What I'm going to do is that memory, or the information from the output of the ALU, is going to be sent back into the inputs in the loop that we have set up. And it's also going to be sent onto the writing bus of the memory so that we can write that value into memory if we really want to. So what happens if the amount of delay from this, for writing back to memory, is so small that when we read it back into the ALU, we can duplicate information that we're going to use in the next clock cycle. So like if we calculated that data in the last clock cycle, we can re-access that with a different core that doesn't have that information yet in the next clock cycle. And if you just think about that, that has so many different coding applications, just because it makes stuff so fast. Like, you don't, you're basically wasting a clock cycle if you just need to duplicate some information and you can't do it for whatever reason. So it turns out that that means that in the other places in the ALU where we have inputs from the memory, we want to make that connection as fast as is possible, because the more delay that we have on there, the less amount of time, or the less memory is available to us that will be available for us to access in that small amount of time. So with that in mind, that's going to mean that the decoding circuit that we use is going to have to be extremely fast and anti-burnout, but most importantly, extremely fast. And what I was trying to do before was I said, you know what, look at this XOR gate right here. You know, it doesn't actually take any inputs from the memory, it just takes inputs from the barrel shifter. Whereas the barrel shifter will take one input from the previous clock cycle, and the number of shifts that the number of shifts that is going to be operated, that information is going to come from memory. So if I have this adding delay onto here, that's going to reduce the overall amount of time that it takes. So why don't I move the XOR gates to down here in front of the barrel shifter so that they don't add any extra delay? I just spent a month trying to find an efficient way to do that. And there may be one. If you have one, I would love to see it because it would be great for me to do this. I came up with a solution, but I had to keep on moving the output over here further and further away from the memory. And that is going to end up adding delay anyway, so I didn't think it was really worth it. And the complexity of it was also just way too much. So one thing that I did optimize a bit was that, oh dear, my game music is on and it's distracting me right now. Anyway though, so one thing that I did do though is that I took the outputs of this barrel shifter and I was able to scrunch them up a bit. I figured I might as well do something with the time that I had, so this is what I have now. It also actually ends up moving one tick of delay from the XOR gate to back here that wasn't there before. So that's very nice. Actually, does it? Yeah, I think it does. Yeah, actually, I'm very sure it does. So in order to make sure that this is 16 ticks, another thing I want to show off is that I added this little setup. So this is a, I guess you could call this a clock, and what it'll do is it has a period of 4 ticks on, 4 ticks off, so I guess you could call it 8 ticks in general. Now the point is that that's a 16 is a multiple of that 8-tick period, so if it's 16 ticks, there shouldn't be any interference, and if we turn this on and leave it on for a long period of time, this should just sync up. Now, I don't actually have the barrel shifter sending anything through, but if I turn that off, then we should see it arriving perfectly in sync. So if you really wanted to test this, what you would do is you would add a whole bunch of repeaters out here to check the period, and that would let you verify that. But as you can see, there's no interference that's being created. By now, it would have this would just be pure on. Maybe it wouldn't actually, just because of the particular setup that I have here. I think because like the backflow comes in, or there's the circuits flowing into here, which could go back there, but if we fix this up a bit, if we break that, it's pretty easy for us to make something using a half slab that just still works fine. Yeah, so maybe something a little bit like this. So there's 3 ticks there, and then the 4th tick comes from the comparator. Lever there, and now we should also be able to see that, again, it's perfectly in sync. Actually, no, it's not. All right then. So it looks like we're only one tick off. It looks like it's a good thing I tested this also, because it looks like we're going to need to add a bit more delay to this. Only question is where. So let's go ahead, turn that off for a second, do a bit of debugging. 1 tick, 2 tick, everything should be synchronized here. So 3 tick, 4 tick, 5 tick, 6 tick, 7 tick. The rest of this is 7 ticks, so that's 15, and that is indeed 1 tick short. So we're going to need to add, adding this delay to this repeater shouldn't actually mess anything up, just because it's still a 2 tick interval. So now let's try that. This also gives us a bit more delay time, should we need it. And let's see if we have any interference now. We shouldn't. And I'm actually going to do what I said and do this. Stack 15. And as you can see, the period isn't changing. It's just 4 ticks on, 4 ticks off, over and over and over again, which means that everything should be perfect. So yeah, that means that everything is synced up. I'm going to move this sort of stuff back into position off camera. Really not the most necessary thing to... Oh dear. I didn't kill that pulse. But, yeah, so I'm not going to show how I ended up building all of this. If you really want to, let's see if I can get a good angle on this. This is sort of how this one works, and then this one and then the one next to it sort of looks like that. So yeah, and then when it comes down to the bottom here, that's on the same block as that, before it goes into here. One semi-important thing actually to note is that in the original design that I showed off, I had the input repeaters to this wire down here. And that has now changed. What I did is I just moved them a little bit up this wire, and that lets them be a little bit closer to the outputs of the thing itself. So if you're running into issues, that could be where it is. Anyway, so that's far enough rambling about ways that I've messed up. Let's actually finally get on to the thing that we're supposed to be doing this video, which is actually building the decoder for this. Alright, so earlier when we were talking about this, before the whole mess happened, we talked about how there are basically going to be 3 bits that we were going to be building for this decoder this episode. The first one was going to be the shifting bit, because for an odd number of shifts, we need to use the adder shifter. So yeah, that just is going to mean that we enable or disable this wire. It's a 1-bit function. All we need to do is invert the wire, and that's that entire process for the decoding done. So cool, we only actually need to do 2 bits of processing for today. And that's just going to be decoding 2 bits for these guys right here, the main barrel shifter. As you can see, right now we've got all of these levers that are already powered, but what we're going to need to do is we're going to need to build a decoder that is going to make it so that only one of these is sort of powered at once, excluding if we're doing something like rotating or get bit. We're going to be talking about how to do a few of those a bit more advanced functions next time, but for now all we need to do is we just need to finish the main part of this decoder. We're going to do like 1 or 2 bits of things that we're going to be talking a little bit more about next time, but that shouldn't be there yet. Yeah, so let's go ahead and see if I can remember how to do this. It's actually been a while since I recorded. Like, I've done enough, spent enough of this video making excuses. Anyway, so let's talk about what exactly it is we're doing right now. So right now we're making the decoder for the 2 least significant bits for this thing right here, which is the 2 most significant bits shifted down to the 2 least significant bits. So this is shift 3 times to the right. So that means that, let's see, for right shifting we said that we're going to do backwards, so that means that we're going to start counting this at 1. 0 shifts is obviously going to be no shifts whatsoever, and it's just going to be sending straight through. 1 shift, however, we're going to treat that like it's -1 shifts for right shifting, as we discussed earlier. So I'm going to say that the side on the right is going to be the least significant bit, which actually means that I need to power this like this, and okay, that's fine. So yeah, we're just going to power that like that, and then for the other one, I'm going to add a repeater here. It's going to be powered in a similar sort of way. So we're going to have these two sort of diagonal wires that are going to come up along like this, sort of like these 4 blocks right here, and these will connect to the ones that are directly connected up to the next one. And what we're going to do is, with this one, we're going to add a hopper. Now, it's very important, actually, that we don't actually make this thing have full power. We're going to talk about that a little bit later, but rest assured that it has to do with the fact that we're not adding a repeater going into this. In fact, you can probably guess that the reason for that right now. In fact, I'll just tell it. Basically, what's going on is that if we minimize the number of items in here, we can actually make it so that we don't need to send a full power signal in here, because the signal that gets outputted won't be able to reach the one input that it needs to reach. So by just using hoppers instead of redstone blocks, we can completely solve that, and that's going to save us a tick of delay. And like we've been emphasizing so much, this decoder is going to need to be as fast as is humanly possible. So anywhere where we can save a bit of delay is probably a good idea right now. So next up, you saw that we went 1 down here, so let's make sure that we go 1 down here. And this time, we've counted backwards once, which is basically counting up once. It's a bit confusing. Maybe I should have started at the top up here where this is state 1, 1, but we're good. So like you'll see that it's going to be a lot easier to see the reason that we're doing this in just a second once we have all of these built, because when we look at the most significant bit, what we're going to see is that what are we going to see? We're going to see that when this is shifted all the way up to here, this is only 2 bits that have been shifted, whereas if we look at this shift, it's 6, so 2 plus 6 equals 8, so that's where every single bit gets sent to in a rotate function. So with that out of the way, we can just set this to state 1, 1. And we are good to go. So I'm going to sort of add this for the rest of them. You're going to notice, I'll talk about this in a little bit, but for the 0, 0 state, things are going to get a little interesting if we continue this sort of trend. So we're going to do something a little bit different from that one. These should actually be 1 lower down. Just to clarify, if it's a repeater, it should be 1 block up. If it's a comparator, it should be 1 block down. That's just the system that we're going with. So yeah, with that out of the way, I'm going to finish building the rest of this, and then we're going to take a look at how exactly, or not how exactly this thing works. There's a few functionality things that we're going to need to add on after that. Alright, so we are back. I've built all of this, and now there's 2 things that we're going to need to talk about. First of all, how to connect this thing up, and second of all, how exactly many things do we need to put into these hoppers, and why does it work? Actually, I think I explained this last time, but the reason that this works is that if we count the number of bits that each layer has to access, this one has to access 2. Next layer has to access 4. Next one 6. Next one 8. But now when we come up to the next one, it's only 6 again because it doesn't shift any further than that. So this one's 6. Next to the top one is 2, and the top one is 1. So notice how as we get further, the total number of cells that we need to access inside of the barrel shifter actually decreases. So because of this, because the signal strength of this powered wire is going to be decreasing at the same rate, every single time that it wouldn't be strong enough to prevent a signal from going through, it's also going to require not as much power to send in. So all we actually are going to end up needing to get the correct number of items into these hoppers is we're just going to need to add enough so that it can reach the furthest one out. And if we look at like this first one, I'm pretty sure if we just put one item in, that, oh no, it looks like we need two. Yep, and now that's powered. So if we come up to this one, we know it's going to be more than two. So that's powered the first one, and I suspect if we just throw in one more, it'll power both of them. Not quite, it looks like. Yeah, it's just barely not powering that, so let's add one more. And now they are both powered. So if we come up to this next one, we can rinse and repeat, 1, 2, 3, 4. And I suspect that we actually just straight up need 5 for this one. Right? Did I not throw 4 in? Yeah, one of them went into the other hopper. So let's look at this one, 4, and then I guess it's probably going to be 5. And then I'll also do it for this one. Still going to use the hoppers, not going to replace them with redstone blocks, just because even though it's the same functionality at this point, consistency purpose, and I already have it as it is, so why bother? This one's probably going to be the same as the bottom one that corresponded to it, so 4, 1, 2, 3, 4. And this needs to be set to subtract mode. Not quite. It looks like it could use one more. Is this? Yeah, these are all good as well. So really, this one's going to need 5? Yeah, it's going to need 5. Wow. Huh. Actually, I guess that makes sense because that's the same as the one that's directly beneath it. This one should need 4 though, right? 3, 4. That's 4. And those are both powered, and then these should need 2 each. 1, 2. And just make sure that that's powered. Yep. And 1, 2. All right. Now, just to make absolutely clear that all of this works, what I'm going to do is I'm going to, let's see, I'm going to add a redstone lamp to each one of these wires, because these should be, no, I think I'm going to add it here actually, because this is going to give it a little bit more time to decrease its signal strength. Maybe I can get away with, yeah, I think I'm just going to put it right here. We'll still be able to see the light, obviously, wherever I put it. It's a bit inconvenient to put those into position. And now if we come up to these ones, this one's obviously not going to be lit up because we haven't actually added the power for it yet. This one, and this one should all be powered. And now, so we said that this was the least significant bit, right? Yep. So this side is less significant. So if we turn that on, we should see that this one is off. And the bottom one is off, which it is indeed. If we turn this one on, then it should be state 1, 1, which corresponds to the one that, why are you still powered? Ah, you can see it's exactly 1 block off from being completely powered up there. And if we look at the top one, it's the exact same story. So now if we take a look at just this state, then I suspect right here, yep, it's exactly 1 block away from powering the repeater, but it's still not quite there. And if we look at this one, same sort of situation. So that proves that all the logic that this thing is meant to do works exactly 1 tick, so long as we have these blocks right here at full signal strength, which I'm just going to make sure that we do by adding some repeaters. Like so. If I can add the redstone. Alright. So this is all for sort of the main decoder, and I'm going to go ahead and break these lamps now. But there's still 2 things that we're going to need to finish before we call it quits for today. First of all, we're going to want to make it so that, let's see, we're going to want to connect up the middle input, because this shouldn't be 0 by default all of the time. We want it to be off whenever there's any state that isn't 0, 0 on it. But if we do the exact same process that we've done for all of these so far, and we do something that looks a little bit like this, you might notice that there's a bit of a problem going on right here, and that is that these two have been ORed together, and that is something that we can't do. even with the signal strength wizardry that we've done already, that's still going to interfere with things, so we can't do it. So what I'm going to do instead is I'm going to, I believe, let's see, trying to remember what I did before. I'm pretty sure I did something not like that, like that. Now you might notice this is powering this. That's easy to fix though. And now we have this thing which is being powered right here. And now what we can do is we can just add some slabs like that, block that off, and that is a perfect OR gate. So that is the functionality of that main one down. And there's just one thing that we need to do now, and that is we're going to add a bit of the functionality that's going to be used for getBit. So like we said earlier, there's two different ways that we can isolate a single bit from a whole bunch of data. First of all, we can shift it so that the bit that we want is in the most significant bit, and then we can use the adder to get a carry out, or which would be interpreted as a shift overflow, and then we can send the predicate back as our result. On the other hand, if the bit number makes it so that it can't go to the most significant bit, it could only go to this bit, what we're going to do is we're going to use the barrel shifter to shift it in the opposite direction so that it comes down to here, and when it reaches down here, we're going to basically just make it so that all of the bits except for the least significant bit are all off. And that way that bit will be isolated, and when we do that we can cover every single situation. So how exactly do we make sure that all the other bits are off? And that's going to be a bit of trickery, because what we want to do, right, is we want to make it so that this is all being shifted to the left, right? Or, yeah, no, not to the left, to the right. So everything, By the way, proof that Minecraft physics don't work, right there. You fall faster than your blocks do. So anyway, where was I? So what we're going to need to do is we're going to need to make it so that we're going to shift it all the way down, and then we're going to want to power the lines inside of the barrel shifter that are preventing this from, or that would enable the wire to go all the way through. The way we're going to do this is, it seems a little bit tricky because it looks like what's going on right here is that we have one wire that's going to control every single bit, but we don't exactly have that situation. Because one of the interesting things that's going on right now is that we can use a little bit more signal strength trickery to our advantage. Because what we could do is we could send a signal strength in here that is strong enough to arrive at this one, but not this one, which controls the two least significant bits. So that's exactly what we're going to do. Now, because of falling, because of similar reasons to these wires, what we can actually do is we can have the power start at one source, and then when it arrives at each one of these, we can just make it so that just lost my train of thought. Let's see, where was I? Ah, yes, because we want the signal strength to be enough to not power this, that is actually the same number of blocks in this direction for every single bit, because all of the least significant bits for each bit shift are all in the same column. So we can actually just have them all on one wire. So what I'm going to do is, it doesn't matter for this one, but for all the other bits, what I'm going to do is I'm going to add a half slab here so that we have a diode. I'm going to have you go up diagonally. And then I'm going to do the same sort of thing right here, right? No, not yet. We do the same sort of thing here, because this is a different place. Right? Yeah, I went one block too short. So now, these are the two wires. We also need to hook up this one. This one's going to get a little bit messier. As you can see, it's getting quite inconvenient to get some wires to go through here. What we're going to do is we're just going to do a little something like this, and everything works. We also need to add that there. And why are you getting powered? I see why you're getting powered. Ooh, that's actually bad. Can we just do that? Yeah, I think we can just do that. Get away with it. Yeah, we can just do that and just straight up get away with it. Yeah, and in fact, now we can start bringing this down. And now this is sort of in the same diagonal as this. So what I'm going to do now is I'm going to turn both of these wires on, like so. Let's add wire, lever there, and lever here. And so now that I have both of these powers, I can see this is the amount of power that these two hoppers are giving off on their own. As you can see, just one short. And now what we're going to do is, we also need to add that to fix those problems. And now we need to find where on this wire we need to power this, such that it also powers this, and this looks to be the spot right here. And now I'm going to turn this off of state 0, 0, or 1, 1, to make sure that this powers. Does not power this wire right here. We need to make it travel 3 more blocks. So what I'm going to do is I think just say that this also needs to be powered from here. And now that reaches right. Yep. So now we're just going to have a sort of situation like this. And no, don't want to break stuff. And sure, this is a bit crude, but it works just fine. Alright, so one final thing, now that we have pretty much everything that we need to do out of the way, is that this system for getting the least significant bit isn't quite effective because this repeater actually ends up powering both of these bits. So when all the other bits are powered except for this one is actually going to send both the least significant bit, which is the bit that we want, and the bit that is one bit more significant than it, which isn't exactly what we want. So how do we just make it so that it's just one bit? Well, I'm going to go with a bit of a brute force approach. So if we look at this wire that's coming out through here, first of all, it will always be this bit, because it's only bits 1, bits 2 that will get passed if we have this lever powered on. So if we look through this one, and we just look at its path, the next thing it does is it goes through this XOR gate. Now, there's 2 ways it can go through this XOR. It can either go through this repeater, or not repeater, but comparator. It can go through this comparator or this comparator. Now, if it goes through this comparator, that doesn't matter because it's getting the exact same signal strength into its cancel signal, so it's just going to get canceled. So that means that the only case that we actually need to worry about for going through this comparator is this one. So what I'm going to do is I'm just going to go here and I'm going to add a repeater. This isn't going to change any of the functionality of the XOR gate, it's just going to make it so that if we want to, we can just send a 0 from this input of the barrel shifter, which is exactly what we want to do in that rare situation. So, it's also very convenient that this right here is the bit that defines how many times we have counted if it's even or odd. So we don't. These are both going to take the same information because We're going to power this depending on whether or not the bit that we're getting is even or odd. So I'm not exactly sure if this and this are inverses of each other or not, but it's something like that, and it's just convenient that they're right next to each other. So with that out of the way, that's all that we need to do as far as raw barrel shifting is concerned. Now, because there's a whole lot more to this, we're going to be talking about a bit more of the other functions in the next episode, where we're going to be finishing off this decoder and hopefully finally getting around to actually saying we're done with the hardware. So yeah, I hope you guys enjoyed, and I'll see you guys next time.